just one slide on. This is the next slide after the one that we're just looking at, and I want to use it to explain the concept of the outlier. So I'll move a little bit back and forth. So before the break, we talked about the percentile, we talked about the range first and then the percentile. And we said that the range is the difference between the minimum value and the maximum value. And then for the percentile, we said that if you assume that there are 100 observations in the data set, and you rank them from the beginning to the end, from the highest to the smallest, from the largest to the smallest, you can find the value that has 25% of the observations below it as 25th percentile, the one that has 75% of the observations below it as a 75th percentile. And I then said that between that 25 and 75th percentile is something that is called the interquartile range. Okay, the interquartile range. So this plot that you're looking at here is called the box plot. It is a way by which we represent the distribution of data, and it helps us to identify outliers. Okay, helps us to identify outliers. So if you had values from the smallest all the way to the largest, and you ranked them like we said to do, okay, and you rank them like we said to do, in the middle, you have something that is called the median. This is at the 50th percentile, okay? And we said that you would have, below that, you have 25th percentile, where there's 25% of the values below. But there's another metric that we're always interested in, which is something called the lower adjacent value and the upper adjacent value. Because what we're really trying to get is where the majority of the data set is located. And we want to know if there are values outside that. If there are values outside that, in much of clinical medicine and public health, these values that are outside are the values that are most likely going to represent bad things. That's where bad things happen, okay? It's pathology, that's where abnormality is. An abnormality is not necessarily bad per se, but that's one way to think about it. So if you look at height, okay, if you look at height, if you got the height of everybody in a school, okay, high school, there will be some kids who are generally very short. And there'll be some kids who are very, very high. Maybe they're the people who are playing basketball in the high school, right? And then there will be some kids in the middle. Those kids who are in the middle, the majority of the students in the class will be here. In the school, rather, will be here. And then you will have some more people who are tall, but they're not exceedingly tall. Okay? The majority of the school will be in the between the 75th percentile and the 25th percentile. But there'll be some people who are tall but not exceedingly tall. There'll be some people who are short but not exceedingly short. Okay? And then there will be people who are dwarfs. Right? And then there will be people who are like maybe just abnormally tall. These people who are abnormally tall, these are the outliers, or these people who are abnormally short, these are the outliers. The same thing applies to the ferritin values that we're looking at. We saw that one person had a ferritin value of 987, while the majority of the data sets, the women in the study, their ferritin values were less than 200. So why does this person have 987? That is highly unusual, and that's an outlier. Okay? There is a formula, and I'm going backwards now, that we use to identify outliers, and that formula is based on the interquartile range, as well as based on the value of the 25th percentile or the first quartile and the value of the 75th percentile or the third quartile. Okay, so if you calculate this value, what you get is the lower adjacent value, this one. Okay, what you get is a lower adjacent value. If you calculate this Q3 plus 1.5 times interquartile range, what you get is the upper adjacent value. Okay, that's the upper adjacent value. And any value that is then greater or less, those are outside values or outliers. And you can illustrate this in box plots. And if you find these outside values, if you're presenting this data set if you're presenting this box plots at a conference, it's very likely that one of the people who are coming to see your poster will say, oh, why do you have these outliers? What do they represent? So you will already have an explanation and say, oh, we had this person who had some genetic disorder, and that's why their ferritin values were so high. Or we had this person who had HIV, and that's why their ferritin values are so high. You know, or maybe there's this kid in my class who has a growth hormone disorder, and that's why they're so tall. You know, so those explanations, that's what the outside value will have you. You have to go back and look at the data and look at the context and interview people and try to understand why this outside value exists. Okay, so box plots are very important, and the more now that you've seen this, you understand what they look like, you're more likely to come across them. It's just the way that learning works. Once you see something and you know what it is, now you start seeing it in nature. Okay, and if you're interested in what these are called, we have the box, okay, and you have the whiskers. So these are also called box and whiskers. Okay, the whiskers are these two lines that lead to the upper adjacent value. And the upper hinge of the box plot of the box is the 75th percentile. The lower hinge is the 25th percentile. And the middle here is the median. And you're going to see some more differences in how the box plot may look in a moment. Okay. Look at this box plot on the right. Think about the box plot that we just saw and pay attention to this box. What do you think is different? Does anyone want to try? Yes, please unmute yourself.
Okay. It looks like it's not evenly divided.
It looks like it's not evenly divided. Excellent. You can see that the line in the middle is closer to the bottom than to the top. You can also see that the whisker here is shorter than the upper whisker. Okay, this is long and this is short. What do you think this means for the data? Do you think this means that the data is skewed or not?
Skewed.
Skewed. Okay. It's because the data is skewed that the box plot is showing like this. It's basically telling you that there's more of the distribution happening in one direction of the data set. Okay, or in one direction of the distribution. And you have the sole outlier out here. So box plots tell you where the 25th percentile is. They tell you where the 50th percentile is. This is 25th, this is 50. They tell you where the 75th percentile is. They tell you if there are outliers, but they also tell you if the data is skewed or not skewed. Yes, question.
Yeah, Dr. Ibrahim, sorry, please. So are we saying that for the box plot, this particular box always gives us the 25th and the 75th percentile. So the box actually represents the interquartile range.
Exactly. It represents the interquartile range.
Always. Okay, so by
Always.
this, we would infer that there are a lot of outliers over the 75th percentile.
Not quite. This is the outlier. Just this one.
Okay.
Okay.
So we are saying most of the distribution is within these ages. That is 30 to around 37, right?
7, yes, precisely. And that the data, so if you were to draw this histogram, if you were to draw a histogram of this distribution, it would look something like this. Okay. And this will be 25. And the median will be 33. So let's say this is 30. And this is 35. And this is, let's say now this is 50. I'm too lazy to write it all out. And 33 will be somewhere here. Okay. So you will draw a distribution that looks like this. Okay. This is what that distribution looks like. I'm not clearly great at using my mouse to draw, so pardon me. But this is what it looks like. And you can see that there's a little bit of a skewing in this distribution. The bulk of the data is from in the 33 and below, because that's where the median is. This median is 33. Half of the distribution is there. And the 25th percentile is 29 or something like that. And so that will be somewhere around here. Question?
So can you look at the box plot and say whether or not the data are right or left skewed?
Yes. So if you know how to infer how the box plot relates to the histogram. So first of all, the question that I have for you is, look at this histogram. Is this right skewed or left skewed?
It's left skewed.
No,
Right
this is
skewed.
right skewed.
Right.
It's right. Right.
This gentler slope is where? Is it on the right or on the left?
Right.
On the right.
Skewed.
Right. Okay. So if the gentler slope, if the gentler slope is on the right, go ahead.
So can I say that even just looking at the box plot, we can infer the skewness of the data. So if the interquartile range is towards the lower, or let me just in lay terms, if the whiskers is shorter towards the 25 percentile, then we are more likely to have a right skew. If the whisker is longer at the lower end, that's towards the 25 percentile, we are likely to have a left skew.
If the whisker is longer towards the upper, in the upper region, this is right. Because it's almost like if you invert this data, right, you invert it like that, almost in a clockwise direction. Okay, you're going to take that's lying flat like this and invert it like this. And so that becomes right skewed, because if you have drawn the histogram, the gentler slope will be on towards the right. Okay, is that clear to everybody? Yeah. Okay. When you
Good
say talk
evening.
about this, yes, please.
Okay.
Good evening.
Yes, my name is Akunna. Thank you for this class. Please, I'm a bit confused about the part where you mentioned that the bulk of the ages fall within 33. Like, I don't understand what you mean by that.
Okay. Okay. No, so that is just colloquial way to describe. 33 is the median. Okay. Do you agree that 33 is the median?
Yes, I do.
Okay. So if 33 is the median, most of the ages are in that region, right? That's why it's the median, right?
Oh, okay, okay.
I mean, so, but in reality, the interquartile range goes from 29 point something to 37. Do you agree?
Yes, yes, I do.
You
Yeah,
do.
yeah.
So that's why that's why I said that the bulk of the observations are around 33. So are you on the same page now?
Yeah, we
Okay.
are same page, but in order to calculate for the outliers or the outside values, I saw you like times by 1.5. Is it a
Yeah,
constant? Is 1.5 a constant value?
it's a constant value. Yes, it's a rule of thumb.
Okay.
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 Yeah, it's a constant value. So if you just plug this number, Q1 minus 1.5 times the IQR, then the value that falls outside of that is an outlier. Okay. All right. So that's outliers. And then we've talked about box plots. And so if you have a box plot, and this is from the actual data from a study among resident doctors in Lagos, and you will come across this data a lot in the course of this study. It's an old data set. We collected this data in 2009, so very old. And this is ages of resident doctors in Lagos at this time. This is the box plots we're just looking at, okay? And we said that the data was skewed, right? And the median was 33, right? And we said that the data was skewed, right skewed. And we have this outlier. Once in a while, you have an older person who comes back to the residency, and maybe they're 50 something, which is fine. But the other thing that you can then do with the box plot is you can subgroup, you can separate out the males and the females in the data set. What can you tell us about this box, this visualization on the right? Anyone wants to tell us what they see?
Okay, from if I may just have a go.
Yeah.
So from the box plot on the left side, we can see that generally the ages are not normally distributed. We have
Yeah.
a right skew, meaning that
Okay.
even though the age distribution is between probably 32 and let's say 38 for the general data, we are seeing on the right side that that skewness may be attributed to the distribution of the ages in female doctors. The age for male doctors is slightly more evenly distributed than female.
Okay.
So we have most female doctors within the ages of 29 and 35, but we have male doctors between the ages of probably 38 and 30. I can't get the numbers now. So just saying that
Okay.
if
So
you look at the subgroups, the distribution of ages in female doctors is slightly skewed, more skewed than.
okay, so let's not talk about the skewing because then it becomes hard to see. But in general, do you think that male doctors are younger than females, or is it vice versa?
Yeah, females are younger generally
Females are
from the
younger
age.
generally. Very good. In general, the second question, do you think that male doctors are more spread out in age than female doctors, or is it vice versa?
Yes, more and more spread.
The males are more spread.
Yes,
So you
male
can
are
see
more
that.
spread out.
more spread out. So you can see that there are 26-year-old males, but you also have 47-year-olds. Okay, and then you have this sole outlier here, right? And the 75th percentile of the males is actually 40 or something like that. Okay, so this is how to understand, or 37, sorry. This is how to understand the box plot. You can use the box plot very easily. You compare one subgroup to the next subgroup, and you can make inferences. Okay. So we spend a lot of time talking about box plots and percentiles. So we're going to change gears and talk about something that's also related in some way, but maybe not as clean. But throughout today, the way to understand the data is to always go back to the histogram and to that normal distribution curve. If you draw a normal distribution, a curve that looks at, so basically a density curve based on the data in the normal distribution in the histogram, that spread, we've talked about how you can look at the range, we've talked about how you can look at the percentile, but another way to describe that spread is a standard deviation. Okay, the standard deviation tells us how spread out the values are around the mean. So for the standard deviation, the focus is really on the mean. Okay, the focus is really on the mean, not the median. Okay, and we're not ranking per se like we have done in the last few concepts that we've looked at. The focus is really on the mean. So we're trying to see, if you look at the example of the ages of resident doctors, the thing that you note is that the ages of the male doctors is more spread out, while the ages of the female doctors is more closely clustered. Okay, if we were to calculate the standard deviation for the male doctors, it will be large. But if we were to calculate the standard deviation for the female doctors, it will be smaller than the standard deviation for the male doctors. So the standard deviation tells us how spread out the data is, and it's one of the ways that we represent the spread, the spread of the data or the dispersion. Okay. There's a key thing to note though, is that the standard deviation is assuming that the data is symmetric. That means that 50% of the population is below the mean, 50% of the population is above the mean, and the mean and the median are the same. If the data is symmetric, 50% of the data is below the mean, 50% of the data is below the mean, is above the median, and the mean and the median are the same. Okay. The standard deviation is measured assuming that this is the situation. And if this does not hold, then we need to think about other things, other ways to represent the data, but it's important to bear that in mind. And there is a formula that we use to calculate the standard deviation, and this is that formula. Essentially, what we're doing is that we take each value in the observation, we subtract it from the mean, and we look at how far that difference of each value from the mean, we square that value, and then we sum it all up, and we divide it by the number of values. In the olden days, when I remember in my first statistics class, we will calculate the standard deviation by hand. And so if you had 20, 30 numbers, you would calculate, so you would take each one, calculate the mean, and then subtract each value from the mean. So if the mean is 33, and each person's number value is maybe 31, 32, 33, you will subtract 31 minus 33, which is 2, 35 minus 33, which is 2, where there's -2 and the like, and then you square. And then when you square that, you sum it all up. It's a measure that then tells you about how spread out. And you can compare the standard deviation. If you have a small standard deviation, it tells you that the data are clustered together around the mean. If you have a large standard deviation, it tells you that the data are spread out. Okay? And you can see how this is represented in this density curves. Here, you have a flat base. The data is spread out. This is the height of children in pediatrics clinic. For standard deviation of 10, the heights are spread out. For a standard deviation of 2, you have a base that is narrower. Okay? This is what standard deviation does. So you can look at these two data sets and understand that in pediatrics clinic, it might be that maybe they're mostly focused on children who are 9 to 12-year-old in this case. While in this case, they might be seeing children whose age goes all the way from 6 to 15. Okay, so this is the way that you will understand the data set. How spread out the data is indicated by the standard deviation. And this is an example that attempts to do that by hand. And you can walk through this using the formula just like I explained. The first thing is you calculate the mean. You take each value, you subtract it from that mean. 38 minus 32.1, 29 minus 32.1, 29 minus 32.1. So that's basically what they did here. Then you take the square of this value, and then you sum all of these together. That's what's happening in the numerator. So what you get from summing all of this together is 98.9. You will divide that by 9 because there are 9 values. Okay, 9. And when you divide that by 9, you get 10.99. You take a square root of 10.99, and the standard deviation is 3.31. Okay? So there's 10 values.
Sorry, sir. You know, 10 values.
There's 10 values. Sorry. And because you did 10 minus 1, that's how you came up with 9. So this is how standard deviation is calculated. And usually when you report the mean in your paper, it is expected most times that you will also report the standard deviation alongside, because the mean will tell us about the measure of central tendency, and the standard deviation will tell us how spread out the values are around the mean. Okay.
So, in case you get data which is abnormally distributed, you cannot use the standard deviation. What else can you use? Because
Very good question.
Okay.
You can use the median. You can use the median and the interquartile range. Okay. If the data is not normally distributed, you use the median and interquartile range. Okay. All right. Excellent. Any questions? All right. So go ahead.
Yeah. So sorry. The previous one. Yeah.
Okay. Sorry. So I'm just looking to see how much further we have to go before we. This one? Or this
No,
one?
yeah. So our standard deviation was 3.31
Yeah.
and our mean was 32.1. So you said the standard deviation represents how data is spread around the mean.
Yeah.
So because the 32 is the edge and the 3.3, so what does it mean? Does it mean that majority is 32 plus or minus 3, or that what does it mean, the exact 3, the spread, I mean the spread of edges?
Yeah. Okay. Good question. When we draw a normal distribution, or let me say that I'm going to come back to your question and I will answer it in a moment. Okay?
Okay.
Because it's something that's going to come up 2 slides from now. What do we mean by a normal distribution? Does anybody know? When we say that data is normally distributed, just a moment ago, I said that, yes, please speak up, yeah.
Thank you. It basically means that if we have a large set of data, it usually assumes a normal distribution, and this is usually common in statistics.
Yeah, okay, very good. You're getting to another concept, which is the central limit theorem. Okay, very good. But before we get to that one, yes, please pick up.
All right,
Say
sir.
hi.
When we talk about normal distribution, it means that most of the times at 98% of the value would fall between -1 and +1 standard deviation.
Okay, all right, you're getting into the nitty gritty. But what does the shape of the normal distribution look like?
It's a bell shaped.
Bell. It looks like an inverted bell, like a bell shape. Okay, we are literally looking at different types of normal distribution here. So you're all right, everybody. You guys want to answer the question, you're right, but you're going into some of the details. Okay, but when you're asked really what normal distribution is, the shape of normal distribution is these shapes that we have been looking at that looks like that, where there is no skewing. Okay, there is no skewing. Okay, the distribution is symmetric. There's no skewing. Okay, so when there's no skewing and the distribution is symmetric, that is a normal distribution. And these are examples of normal distribution in data. This is distribution of diastolic blood pressure. Okay, in this case, it's wrongly labeled. This should be diastolic blood pressure. The mean is 80, and you have people with diastolic blood pressure going as from 64 all the way to 98, but it's normally distributed. The mean is 80 and the median is also 80. Okay, this is the distribution of male heights, maybe of children, and the mean is 69, and you have people going from 61 all the way to 79. And the mean and the median are the same. There is no skewing. You can see that this is broad-based. This is broad-based, but we have this narrower normal distribution, and this is the returns from the S&P 500. Okay, which is, if you know stock market, maybe you'll be familiar with this concept. But this is a narrower normal distribution. Okay, it's not broad-based like this one, but it's still normal distribution. The mean and the median are the same, and the values are symmetric. The distribution is symmetric. There is no skew. Okay, all right, that's a normal distribution, and this is what the normal distribution looks like. And this normal distribution is symmetric. Remember I said that. And it's unimodal. I have not said that. A unimodal distribution means that it has one mode. This is the mode. If you have a normal distribution, the mean, the median, and the mode are the same. Okay? Then the distribution is symmetric like that. When you have this situation, you can split apart the standard deviation. You can split apart the curve or the graph on its x-axis based on the standard deviation into a scenario where the bulk of the data is covered by 6 measures of the standard deviation, where 3 measures of the standard deviation will be above the mean and 3 measures of the standard deviation will be below the mean. So if the mean is 32.1 and the standard deviation is 3.3, this is 1 standard deviation. This is 2 standard deviation. And this is 3 standard deviation. So if somebody tells you that the mean is 32.1 and the standard deviation is 3.3, so you can assume that 32.1 minus 3.3, let's say that is 29. I don't want to do the detailed calculation. And 32.1 plus 3.3, let's say that is 35. It means that 68% of the data lies between 29 and 35. And the mean is here, 32.
Sorry, please say that again.
When we have the mean of 32 and the standard deviation is 3, okay, we can subtract 3 from 32, we get 29. We add 3 to 32, we get 35. What we're saying in essence is that the majority of the data, 68% of the data, lies between 29 and 35. That's really what we're saying. So that's why just by seeing the mean and the standard deviation, we have a mental sense of, oh, this is where the bulk of the data lies. It's akin to what we saw with the median and interquartile range, where we said that the majority of the data lies between 25th percentile and the 75th percentile. Okay? But here, because the data is normally distributed, we're not stuck with the interquartile range. We have an option of looking at even larger amount of the data, which is 68%, and we can say that 68% of the data lies between -1 standard deviation and +1 standard deviation. And because in our example, the standard deviation was 3. Okay? And if we want to know what the 95th percent of the data covers, or 95% of data covers, that is from -2 standard deviation to +2 standard deviation. And so 32 minus 6, because 2 times 3, 32 minus 6 is 24, or is 28. Or what is it? is 26. 32 minus 6 is 26. 32 plus 6 is 38. So if somebody asked you, and somebody said the mean of this data set is 32, and the standard deviation is 3, I'm trying to know what the 95% of the population, what's the age range? Then you can easily say, oh, it's from the plus two standard deviation to minus 2 standard deviation, which is approximately between 26 and 38. Okay, so that's the power of the standard deviation. Just by knowing the mean and the standard deviation, we can understand where the majority of the data set lies. And we can even go further, and if we want to know what 99% of the population covers, that's from minus 3 standard deviation to plus 3 standard deviation. One thing I want you to note is that these values that I have been mentioning, they're ballparks. Okay? In reality, plus 1 standard deviation is 68.2%. Plus 1.96 standard deviation is 95%. Okay? Plus 3 standard deviation is 99.7. So when you have a normal distribution curve that looks like this, you can understand where the majority of the population lies just by knowing the mean and the standard deviation. Okay? All right, any questions? Or is this perfectly clear? Or you're completely lost? Is Peter? Yes, question.
Okay, so thank you very much. I think I've tried to get an understanding, but I'd like to reiterate for clarity to make sure that I understood it well. I'll
Yeah.
use the example of 10. If my mean is 10,
Yeah.
okay, and my standard deviation is 3,
Okay.
okay, does that mean that 99.7% of the observations lie between 7 and 13?
The standard deviation is 3.
Yes.
So that means it's here. That means that this value of 3 of standard deviation tells you that minus 1 standard deviation is at the value of 7. Minus 2 standard deviation is at the value of 4. Minus 3 standard deviation is 1. Plus 1 standard deviation is 13. Because the standard deviation is 3, right? Plus 2 standard deviation is 16. Plus 3 standard deviation is 19.
Ah, okay, I've got
Okay.
that. Thank you so much.
Thank you so
Then
much. Very
what
good.
does standard deviation of greater than 3 mean? Like if you have like 5 or something.
Ah, very good. So if you have a standard deviation of 5, i.e. the standard deviation of 5, or do you mean 5 standard deviations? There's two different concepts. So do you mean 5 standard deviations, as we said here, or a standard deviation of 5? So if you say a standard deviation of 5, I'm going to show you in a moment. Let me erase all the ink on the slide. For a mean of 10, okay, and standard deviation of 5, it means that plus 1 standard deviation is 15, plus 2 standard deviation is 20, plus 3 standard deviation is 25. Minus 1 standard deviation is 5. Minus 2 standard deviation is 0. Minus 3 standard deviation is minus 5. If you have a variable that cannot take the value of minus 5, your distribution will not be normal, it will be skewed. Let me say that again. If the standard deviation is 5 and the mean is 10, but the variable cannot take the value of minus 5. An example is maybe hemoglobin or age. Let's say age. Right? You go into an elementary school and you have kids, and let somebody says to you, maybe they've put together, let's say you come to a church and you go into the kids section of the church, okay? And you measure the ages of the kids in that church, and you get a mean of 10. This is perfectly reasonable. And the standard deviation of 5. In this scenario, you cannot have an age of minus 5. It's not likely for that distribution to be normal. What is more likely is you will have a distribution that looks like this. You have so many kids whose ages are around that 10, but then it gently goes like that. This distribution will not be normal. And which kind of makes sense once people start getting to like 12, they stop coming to religious organizations. Teenage years setting, and then once he's 18, there's more fights to bring them. Okay, so if you had a standard deviation of 3 for a mean of 10, it could be normally distributed. But if you have a mean of 10 and the standard deviation of 5, it's not likely to be normally distributed. So these are the kind of information that you can get from the data. If the mean was 100 and the standard deviation was 5, obviously it can be normally distributed, because then this would be 95, 90, 85, which are all values that are possible. Is this clear? All right. So this is some more opportunity for you to take more look at the question. Okay. When we derive reference ranges, if you assume that you're the person who has discovered blood pressure for the first time, you're this scientist, you've been doing a lot of work, you discovered blood pressure, or say you go into an island where humans had never come before, or where modern people who are, there's never been doctors or nurses there, and you're the first person who's going to describe the blood pressure for that population. You measure the blood pressure for all the people there, and you want to come up with a reference range. If you measure the blood pressure, you're likely to get a normal distribution. That normal distribution helps you to know, like if you have values that are on the extreme ends, they're likely to be abnormal. If you have a person whose blood pressure now is like maybe the systolic blood pressure of 50, right? That's likely to be abnormal. Or systolic blood pressure of 200 and something, that's likely to be abnormal. But you would expect that the majority of the population, their blood pressures will lie between this -1 standard deviation and +1 standard deviation. And the same thing applies to height as well, right? So we've talked about this as an example we've seen before. We're going to wrap up in a few moments, but there's one concept that most people will deal with when you start doing analysis, which is that when you're converting from one unit to the other, you have calculated the standard deviation. Let's say that you have calculated the standard deviation for height in meters, and you need to convert it to centimeters. What do you do to the standard deviation? If you multiply by 100 for meters to get centimeters, all you need to do for the standard deviation is also multiply by 100. You will find this useful, as you go along, but generally, whatever you do to the mean, to change from unit to unit, you do it to the standard deviation, and it's the same value. Okay? So I'm going to stop here. I'm not going to explain standardized normal distribution. We can take that as we go along. And in future sessions, we'll talk about standard error. And if it becomes necessary, we can talk about the standardized normal distribution. Any questions? We have about 5 minutes to take questions.
Yes, sorry, I just wanted to ask.
Yes.
I just wanted to ask quickly. I see that the way these slides were structured, we were meant to actually cover the entire topic within the 2 hours, right? But I mean,
Yes.
we move at a pace at which people assimilate the concept. So, what is the plan to? Because this is very, very important, and I feel so happy and honored to be here because having dealt with data for years, I'm only finally getting a good grasp of this concept before now. Before now, I would just look at a box plot and really didn't know the reason behind people using a box plot and interquartile range in paper and why people use mean as standard deviation, right? Even though you understand what they mean. So, is there a plan? Is an appeal plan to maybe have some ad hoc plans to cover up this topic? That is assuming that the next tutor will not just start with the next topic that you have planned for us. I think it's these basics will lay the foundation for us to understand the greater concept as we move on. Yeah.
Thank you. Good question. So we will incorporate the final slides from this session in the next session and ask the tutor to take that first, okay, before going to the next one. Okay, so we'll sort of build on this one before we go. Okay, Debbie.
Thank you. My question has to do with whether or not, when you have a data set that is normally distributed, so the mean and the median are the same, would the interquartile ranges in any way coincide with the standard deviations at all? And if so, how? Or they're completely not related?
They're not usually related. You wouldn't expect them. There are ways that they might be the same, but because they're really measuring different things, okay, it's very unlikely that it will be the same. The scenario where they might be the same is if there is bunching of data where the distribution is narrow, okay, and there isn't much spread. That's where you might think, okay, potentially the standard deviation, the limits of +1 standard deviation, plus or minus 1, and the interquartile range could be the same, but it's quite unlikely that you'll see that in practice.
Thank you.
Okay. All right. Yeah. Humphrey.
Thank you so much, Dr. Ibrahim, for sharing your knowledge. So I just wanted to ask, we have group data. So far, you've only been on non-group data. Are we going to get also insights on the same?
Insights on, I didn't get that. What kind of data?
grouped data, like for
Yeah,
example, standard deviation for group data, mean for group data, median for group data,
yeah,
which is
exactly. So
different.
we're going to get to that. We're going to get to that in future classes. Okay. Yeah. All right. Akuna.
Thank you.
Yeah.
Hello. Thank you once again for your time. Okay, I wanted to ask, for the standard deviation, the ones that are minus, that are on the negative side, like -3 standard deviation, and the ones that are on the positive side, like, can you explain it with, like, in practical terms, what they entail? Like, when you say the standard deviation is -3 in a, maybe from a data set, or +3, like, what am I, what I don't know.
The concept of -3 standard deviation and +3 standard deviation is conceptual. Most times you will never report -3 and +3 standard deviation in your analysis. What you will report is the standard deviation, and you will then have at the back of your mind that this is where -3 standard deviation will be, and this is where +3 standard deviation will be. Or if somebody else was reading your paper and saw that you said that the mean of the distribution of hemoglobin is 12 and the standard deviation is 1, that person will be able to picture that -3 standard deviation for your population is 9, because 3 times 1, right? And +3 standard deviation for your population is 15. And I therefore expect that the majority of your study, the hemoglobin values go from 9 to 15. You will not have to report the standard deviation and say, oh, the standard deviation is -3, or the standard deviation is -3 standard deviation. No. So the concept of -3 standard deviation and +3 standard deviation, for the majority of the people, for the majority of the analysis that you will deal with, is conceptual. There are situations where you will need to report the -3 standard deviation, +3 standard deviation, and there are situations where that happens. And an example of that is in child growth. Okay, child growth. So if you're dealing with something like the height for age, but in that case, what we'll be looking at are the z-scores, and so there are standard curves that we will be comparing with, and we'll look at how the person falls on those standard curves relative to the standard curves. So for the majority of the analysis that you will do, you will not need to report what the -3 standard deviation values are. We go through this so that you can understand what is happening in the back end. And for if you're reading a paper, you can use it to picture where the bulk of the data lies.
Okay. May I reiterate what you have said already?
Yeah.
Okay. So now, for example, if I'm measuring I have a data set for a group of students, and the mean age is 20 kg, and my standard deviation is 3, it means that the range of ages, range of ages will range from 17 to 23 kg, 17 kg to 23 kg. Is that what you mean?
No, it means that the 68% of the observations, 68% of the observations will fall between -1 standard deviation and +1, which is basically what you just said, 17 to 23 kg. It's not the range, because we said that the range is the minimum and the maximum.
Yes.
Right? So what we're saying here is that 68% of the observations will go from 17 to 23, because the mean is 20 and the median and the standard deviation is 3. Okay? But we can also understand that minus 3 standard deviation, which is 20 minus 9, which is 11, and plus 3 standard deviation, which is 20 plus 9, which is 29, that the weights of the children will go, that 99.7% of the weights of the children will go from 11 to 29.
Okay.
So you will understand that on the back of your head.
Okay.
Okay.
Okay. Okay.
All right.
Thank you.
You're welcome. Any other questions? Excellent. All right. Thank you very much, everyone. So we'll see you tomorrow for SPSS, and next week for R. Next week on Saturday for R, and then we'll continue the sessions. Don't forget, we have Google Classroom. We have someone who is helping us to man Google Classroom, and from time to time he's going to go on there and take a look and